Okay, so if everyone is ready, by your permission, let me start with today's talk, which is about detecting faint signals from outer space using superconductors. Well, why do astrophysicists love faint signals, right? Because normal signals, which can be easily detected, there's a plethora of these signals outside, right? And very good galaxies and space star clusters can be imaged with good signals. But why do we need faint signals, which sometimes may not be detected or can be ignored by detectors and can be taken as noise? So, why are we so interested in faint signals? For that, I would love you to look at this picture, which I attached here. This is W49b. It's a supernova remnant, which has been imaged by CRISM mission, which is an initiative by JAXA, the ISRO equivalent of Japan. And this supernova is very unique because it did not collapse in the usual way that we physicists know. That means none of the models that we have until today are able to fit the process of this supernova. This supernova has actually been formed by an explosion rather than a collapse, and it gives out something known as peculiar X rays, which is peculiar because these X rays are very faint, weak, and transient, which means they are periodic, not very regular. And as far as physicists can think about, these signals probably are given out by black holes. So, faint signals, I agree, but they could be really important. They can come from black holes, literally. And when I was very young, starting to study these in the beginning, I always thought, how could people click pictures of black holes? Like that thing never emits anything, it's black, right? Or it has very low radiation. So how can scientists even image that kind of thing? So yeah, faint signals are kind of those signatures which black holes leave away so that physicists can image them. So let's dive into what are faint signals and how can we detect them. Today's talk is mostly going to be on the kind of detectors, the kind of sensors required to image and extract information out of these signals. So these are my session highlights. I would be talking about the why of pursuing faint signals, which I think I have motivated a bit already, and also why superconductors and not any other material to make such detectors. And then we have the hero of today's talk. It's transition edge sensors, and we'll be talking all about how they are so good and how can they help physicists probe very, very extreme situations in the outer space and what promises TES sensors give. And at the end, I'll be giving a brief introduction to KEK and KUP. Those are the research laboratories that helped me learn a little bit about these physics. So let's get straight onto it. And again, if you have any questions, please stop me and ask me right away. All right. So why should we pursue faint signals? Just like I said, peculiar X-rays are actually something that comes out from black holes. So they are a direct link for us to look at black holes, or at least trace them. Similar such signals exist, like hydrogen 21 centimeter line. This is a very famous kind of signal that comes from neutral hydrogen atoms because of some quantum mechanical effect, which is like spin alignment of electron and proton. I won't go into details. These kind of things actually are found only in the H1 region of the interstellar medium. So hydrogen 21 centimeter line gives us a a mapping of what is the hydrogen distribution of our interstellar medium. And even I have heard that hydrogen 21 centimeter line has actually helped us confirm that Milky Way is a spiral galaxy. So it's very interesting. And similarly, you can see there is Perseus galaxy, which is also an X-ray source and also emitting weak signals. And this is the picture of a radio telescope, which is primarily used to obtain such faint signals, or maybe even CMB. Now, CMB is our prime target, and at KK, we have been targeting CMB the most. And it's so famous, right? Cosmic microwave background. Who hasn't heard of it? So I would like to ask my audience, if it is possible, do you know why cosmic microwave background is so famous? Like, what does it tell us about the universe? Do you have any idea? You can unmute
Anyone?
yourself and let me know.
Yes. If anyone would like to go, please, or else I can add something.
I'm sorry, I didn't follow it. Can you please repeat it once again, maybe?
Oh, it's a simple question. Why is CMB so famous? It's cosmic microwave background. Why is it so famous?
Okay. Just in the interest of time, like I suppose it's like the picture that we get, like the CMB that in the microwave thing.
Mm-hmm.
The red portions are basically the heat, like the reheated regions that still exist, like from the beginning of the universe, right? And the blue ones are cooled regions. So basically, it those are it helps us understand the beginning of the universe. Like this is that picture, kind of, right?
Yeah, exactly. It tells us about the beginning of the universe. Yeah, it's the oldest light of the universe. So, what happened is when there was this Big Bang, before everything could expand out, there was this small cluster where electrons and protons and ions and whatever you can think of were there in scorching heat. Okay, so even light, even photons were there inside, and they were reflecting off one another, and this was this confused little region of extremely high temperature. Now, since light was already reflecting inside of it, we could not see anything because this was essentially opaque. So no light was escaping out of this small, what, plasma or some cosmic soup in the beginning of the universe. But as the universe started to expand, there was more space and the temperature decreased. So these photons could actually start reflecting off from the electrons and traveling far away. So the photons could now escape from that small region. So we could ultimately see what was happening in the earlier universe. Of course, we weren't there. These photons were emitted at that time, and they traveled and traveled ever so long, and they got stretched and stretched. They were emitted as gamma rays, but now after getting stretched, they have ultimately become microwaves, and we have been able to detect them. So these guys, they tell us a lot about how the universe was before, during those expansion times. Because while the light was reflecting, when it reflected the last time and then finally set out for its journey, that was when its polarization changed. And the two things happened. Density fluctuations is what we call it. Density fluctuations led to one kind of polarization, whereas gravitational waves led to another kind of polarization. So there is this specific term called B mode polarization of the CMB, which is a very faint signal once again, which is what we try to detect. And imaging these may, in fact, lead us to gravitational waves that existed when the universe was just starting out. And that could be traced back to even black holes, which were there during the beginning of the universe. So very, very interesting stuff. And that's why the detectors that I will be talking about today are especially very, very helpful to detect CMB. Now, I think in this previous slide, you see, I have written down this energy in electron volt. This is the energy of CMB or radio signals, any such signal like that. So 0.00000, maybe there are 6 zeros and then a 6 electron volt. Whereas our normal visible green light is just 2.5 electron volt. So you can understand how very weak this is. This is so weak that when it was first detected, it was taken to be white noise. So an ignorable white noise, but has such a lot of potential to give us the image of the universe. And in fact, these CMB radiations were first detected by horn antennas. And, the scientists, Penzias and Wilson, what they did, they thought that these radiations were just noise. They were caused by bird droppings. So they just went and washed their horn antennas time and again. But no, they are not any noise. They are so uniform in every direction. How can noise be uniform in every direction? So yeah, now we know it is CMB, and it is very essential for us to develop very sensitive devices, such as sensitivity having around 10 to the minus 19 electron volts, so that we can image CMB. And superconductors enter here. This is what they do. So what are superconductors? Those things, those materials which have zero resistance. But the zero resistance happens only in very low temperatures. Okay. So as I have attached a plot here, and this is the picture of the sensors having superconductors that we worked on. These are very, very sensitive, very specific. There is just one temperature below which it's a superconductor and above which it is a normal conductor. So the resistance change is very sharp, as you can see from this curve here. You see, the resistance was 0, 0 around, and suddenly at one time, at one temperature, it just shoots up to a high value. This is what is the speciality of superconductors. So these temperatures are actually very dependent on outer temperature. So suppose like this is the structure of a transition edge sensor, because transition edge sensors lie on the edge of being a normal conductor and a superconductor. So suppose, as I have shown you in this structure, that there is titanium. Titanium is a superconductor, and a layer of titanium film is present on which you have some photons coming in. They deposit their minimal energy, due to which there is some heat generated. And this heat can even lead to this transition from superconducting to normal conducting. So you see here I have this plot with temperature. You see, as we have increased the temperature just from 0.46 to 0.48, so how much is that? Just 0.02 Kelvin shift in temperature. But look at the resistance change from 0.001 ohm to 7 ohms. So this is a very drastic and clearly visible change in resistance of the detectors. So we can now trace whether a photon was present on the surface of the sensor, right? If we suddenly see that the sensor has increased in resistance, we have resistance measuring devices. If those devices show that the resistance has suddenly shot up, we can understand that, oh, maybe this is the photon that has come in. So this way we can detect even single photons of faint signals. And now you will say that, okay, but this is titanium, and titanium just has a particular temperature beyond which it is a normal conductor and below which it is a superconductor. So, but our weak signals have a lot of range, right? Many different energies. How can we make sure that our sensors are tuned to those signals? Right? If my photon has very less energy, what if this critical temperature is not as low? What if my photon gives some energy, but it's not enough to cause the transition? Will my sensor not be able to detect my photon? Well, for that, we can use some methods. We can engineer our transition edge sensors so that it becomes it becomes sensitive to even lower temperatures. So what we did in our lab was we added a layer of gold in varying thickness. You see, 1:3 thickness, and then 1:5 thickness. And what you can observe from these graphs is that when there was only titanium, the critical temperature was pretty high, 0.48 Kelvin. And as we started increasing the layer of gold, it fell down to 0.17 Kelvin. So that's a nice little push that we gave it towards the lower end of critical temperatures. Now our transition edge sensors can even detect lower energy photons. So this happens because of an effect called proximity effect. And now whether chemistry background may know probably how superconductors work and all about those Cooper pairs and BCS theory, and why proximity effect actually allows tuning of critical temperature. We can lower the critical temperature using a very good conductor on top of a superconductor. So this is some very technical stuff, and this is where I have written down all the differences. And not only does the critical temperature change because of adding a layer of gold, it can also change based on how my transition edge sensor was created. So there are different methods. There is evaporation and sputtering, and so far sputtering was winning in bringing the critical temperature down. Again, these results are only based on around 10 samples, so they are not very conclusive, and we need to keep working on characterizing such TES sensors. And here is a plot that we had when we compared our results of how much we could bring the critical temperature down based on what ISA's JAXA was able to produce, what Esron in Netherlands was able to produce, and what we at QUP were able to find. So yeah, and then there is this orangish line you see. That is the critical temperature required to detect solar axions. And solar axions, you probably know, are dark matter candidates. So we really look forward to detecting things like that, very low in energy but very exotic particles and very exotic signals, which can lead us to very, very rich physics.
Srijita,
Yeah,
sorry to like interrupt here.
yes.
Can we just like wrap it up in a few minutes? Like we just have so that we can have one or two questions as well.
Yeah, we
Sure,
are almost at the end.
sure, sure.
I will
Uh-huh.
just give a small intro about
In
what
two
is.
to 3 minutes, if we can wrap it up, it will be
Yeah,
great.
okay,
Yeah, thank you.
definitely. Dilation refrigerator. Yeah, so I was talking about very, very low temperatures, but how can we maintain such millikelvin kind of temperatures in our laboratories or in big space missions? That is what a dilation refrigerator can do. This is the picture of a dilation refrigerator, and I will be linking some of the informative documents so that you can keep reading further. So this is the picture of a dilation refrigerator. This is the first picture here is the lowest flange, lowest stage, where we put our sensors, and that is the coldest stage where it is able to sustain the cold temperature that is required for operating transition edge sensors. And these are some of the success stories of TES, some of the missions. I will just name them because of the lack of time. And here are links, which I would be sharing with you. And these are like CRISM mission, Hitomi, Lightbird, Athena, Bicep. These missions are heavily based on transition edge sensors, and they are working towards detecting those faint signals, which I talked about. And these are some of the references and credits that I used in my PPT. And this is a bit of a picture about KK, the laboratory where I worked and learned so much about TES sensors. And KK is actually about particle physics and also a bit about astroparticle physics. So this is Kobayashi-san. He is a Nobel Prize winner. He is the person behind the quark flavor mixing. So it's about particle physics. And this laboratory, KEK, was responsible for bringing this man his Nobel Prize. And this was my group, and I was working at the Fuji Gokan, Fuji building, and in close collaboration with JAXA. So this is a small picture of my group. And that brings me to the end of this talk. I really hope I didn't take too much time. If you have any questions, I would like to answer them. Thank you so much.
Thank you so much, Srijeeta. So, dear team, now the forum is open for.
Thank you, Srijeeta. A quick question from my end. Others can please add. Can you just discuss a bit more about the solar axions, like as dark matter detecting, like how are they detected basically?
If we are talking in the context of transition edge sensors, then it is the same. Transition edge sensor has the same working principle that if a particle or a photon is being hits on top of the sensor, then there will be a change in temperature of the operating temperature of the sensor, which will lead to a change in resistance. And this change in resistance will be detected by resistance detectors. So I think the same principle of TES working applies for solar axions as well. And it can be applied to even optical or X-ray photons as well. So if we are using TES, it's the same working principle.
Okay. And would you just like to share with our teammates, like if somebody might be interested in astroparticle physics and all, or like somebody's colleague. So how did you, let's say, involve yourself into this project so that they can also maybe use the same path or a similar path to move in this direction?
For me, it was quite a strike of good fortune, maybe, because my teacher my mentor works in particle physics, and KEK is very famous for its Sokendai KEK Tsukuba J Park summer student program. So their summer student program consists of students. They take students and they give projects to them, and there are many different departments where they work, and it's mostly particle physics related. And the specialty of KK is departments like QUP or IPNS, where they work on astroparticle physics. So that was the channel through which I went, but there are many more channels. You can visit the QUP page where they have such internships, even long-term internships where they prefer postdocs to work with them and give them opportunities. And if you're looking for younger students in bachelor's or master's, this is a very good way to get involved and get in touch with these researchers. So I think, yeah, that was the way I went.